Have you ever wondered what makes up the world around us? Everything, from the air we breathe to the food we eat, is made up of tiny particles called atoms. These atoms combine in specific ratios to form molecules, the building blocks of matter. To understand the language of chemistry, we need to understand these building blocks. That's where moles, atomic and molecular weights, and empirical and molecular formulas come in. These concepts may sound intimidating, but don't worry. They're simply tools that help us measure and describe the world at a molecular level. In this essay, we'll break down these concepts into bite-sized pieces, making chemistry fun and easy to understand. Hey there, science fans! Get ready to unlock the secrets of the molecular world. Atoms are incredibly small. So small, in fact, that we can't even see them with a regular microscope. This makes it tricky to weigh them individually. That's where atomic weight comes in. Atomic weight is the average mass of an atom of an element. It takes into account all the naturally occurring isotopes of that element and their relative abundance. You can find the atomic weight of an element on the periodic table. It's usually listed below the element's symbol. For example, the atomic weight of carbon is 12.011 atomic mass units. This means that, on average, a carbon atom weighs 12.011 AMU. Now that we know how to determine the weight of individual atoms, let's see how to calculate the weight of entire molecules. This is where molecular weight comes in. Molecular weight is the sum of the atomic weights of all the atoms in a molecule. To calculate the molecular weight of a compound, simply multiply the subscript of each element by its atomic weight from the periodic table and add up the results. You might want to get out a sheet of paper and something to write with. Periodic table and calculator, or even a notes app could do for these next calculations. You will use this periodically throughout the video. Let's take the example of acetic acid, which has the chemical formula CH3COOH, to calculate its molecular weight. Firstly, break down the molecule. 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. And then multiply the number of atoms of each element by its atomic weight. Carbon 2 atoms times 12.011 AM. U per atom equals 24.022 AMU. Hydrogen. 4 atoms times 1.008 AMU per atom equals 4.032 AMU. Oxygen. 2 atoms times 15.9994 AMU per atom equals 31.9988 AMU. And lastly, add the weights together. 24.022 AMU plus 4.032 AMU plus 31.9988 AMU equals 60.0528 AMU. Therefore, the molecular weight of acetic acid is 60.0528 AMU. Let's try another example with sulfur. Sulfur exists as a molecule with 8 sulfur atoms bonded together. First of all, since there are 8 sulfur atoms, 8 atoms times 32.06 AMU per atom equals 256.48 AMU. The molecular weight of S8 is 256.48 AMU. Ionic compounds are formed by the electrostatic attraction between oppositely charged ions. They don't exist as discrete molecules like covalent compounds. Instead, they form a crystal lattice structure. For ionic compounds, we use the term formula weight instead of molecular weight. Formula weight is calculated the same way as molecular weight, by summing the atomic weights of all the atoms in the compound's formula unit. Wait, don't put away that sheet of paper just yet. Let's take the example of ammonium sulfide, NH4, 2S. Firstly, break down the formula unit, 2 nitrogen atoms, 8 hydrogen atoms, and 1 sulfur atom. And then, multiply the number of atoms of each element by its atomic weight. Nitrogen, 2 atoms times 14.007 AM. U per atom equals 28.014 AMU. Hydrogen, 8 atoms times 1.008 AM. U per atom equals 8.064 AMU. Sulfur, 1 atom times 32.06 AM. U per atom equals 32.06 AMU. Lastly, add the weights together. 28.014 AMU plus 8.064 AMU plus 32.06 AMU equals 68.138 AMU. The formula weight of ammonium sulfide is 68.138 AMU. Remember, whether we call it molecular weight or formula weight, we're essentially doing the same thing, adding up the atomic weights of all the atoms in a given chemical formula. Next up, the mole chemistry's counting unit. In chemistry, we often deal with incredibly large numbers of atoms and molecules. Imagine counting out individual grains of rice to make a giant pot of fried rice. It would take forever. To make things easier, chemists use a special counting unit called the mole. Just like a dozen always means 12, a mole always represents a specific number of particles. That number is Avogadro's number, which is approximately 6.022 times 10 to the power of 23. That's a huge number. 1 mole of any substance contains 6.022 times 10 to the power of 23 particles of that substance. So, 1 mole of carbon atoms contains 6.022 times 10 to the power of 23 carbon atoms, and 1 mole of water molecules contains 6.022 times 10 to the power of 23 water molecules. The mole is a crucial concept in chemistry because it allows us to relate the macroscopic world, what we can see and measure, to the microscopic world of atoms and molecules. Mole mass particle conversions. Navigating the molecular world. In chemistry, it's essential to be able to convert between different units of measurement. For example, we might need to know how many grams of a substance correspond to a certain number of moles or how many molecules are present in a given mass. To do this, we use conversion factors that relate moles, mass, and the number of particles. Here are the key conversion factors. 1 mole equals the molar mass in grams. The molar mass of a substance is numerically equal to its atomic, molecular, or formula weight. 1 mole equals 6.022 times 10 to the 23rd particles. This is Avogadro's number. These conversion factors act as bridges, allowing us to navigate seamlessly between the macroscopic and microscopic worlds. Let's look at an example. How many grams are there in 2.5 moles of water, H2O? First, calculate the molar mass of water. 2 times 1.008 grams per mole of hydrogen plus 1 times 15.9994 grams per mole of oxygen equals 18.0154 grams per mole. Next, use the molar mass as a conversion factor. 2.5 moles of H2O times 18.0154 grams, H2O per 1 mole, H2O equals 45.0385 grams of H2O. Therefore, 2.5 moles of water weigh 45.0385 grams. Avogadro's number, a really big number. Avogadro's number, 6.022 times 10 to the 23rd, is a mind-bogglingly large number. It's hard to wrap our heads around just how big it really is. To put it into perspective, imagine you had 6.022 times 10 to the 23rd grains of sand. That's more grains of sand than there are stars in the observable universe. In chemistry, Avogadro's number is essential for converting between moles and the number of particles. It's the bridge that connects the macroscopic world we experience to the invisible world of atoms and molecules. From grams to molecules, a step-by-step guide. Let's walk through an example of how to calculate the number of molecules in a given mass. Still have that sheet of paper out? How many molecules are there in 50 grams of carbon dioxide, CO2? First, calculate the molar mass of CO2. 1 times 12.011 grams per mole of carbon plus 2 times 15.9994 grams per mole of oxygen equals 44.0098 grams per mole. Next, convert grams of CO2 to moles of CO2 using the molar mass. 50 grams CO2 times 1 mole, CO2 per 44.0098 grams. CO2 equals 1.136 moles of CO2. Finally, convert moles of CO2 to molecules of CO2 using Avogadro's number 1.136 moles, CO2 times 6.022 times 10 to the 23rd molecules. CO2 per 1 mole CO2 equals 6.84 times 10 to the 23rd molecules CO2. Therefore, there are approximately 6.84 times 10 to the 23rd molecules of CO2 in 50 grams of carbon dioxide. Calculating mass from moles. Turning the tables. We can also use the mole concept to calculate the mass of a specific mole amount of a compound. What is the mass of 0.75 moles of calcium chloride? Cal2? First, calculate the molar mass of Cal2. 1 times 40.078 grams per mole of calcium plus 2 times 35.45 grams per mole of chlorine equals 110.978 grams per mole. Next, multiply the number of moles by the molar mass. 0.75 moles. Kcal 2 times 110.978 grams. Kcal2 per 1 mole. Kcal2 equals 83.2335 grams. Kcal2. Therefore, 0.75 moles of calcium chloride weigh 83.2335 grams. These calculations highlight how the mole concept allows us to connect the mass of a substance to the number of particles it contains. So, the next time you find yourself solving a mole problem, remember that you're not just crunching numbers. You're developing skills that have real-world significance. Keep practicing, stay curious, and never underestimate the power of chemistry. Thanks for joining in on this journey through the molecular world. Don't forget to like, subscribe, and hit the notification bell to stay updated with the latest videos. See you next time, and keep exploring the wonders of chemistry. Be sure to have a nice night and good night.